Welcome to today's Research Pays Off, and I will now hand it over to our speaker, Dr. Kamal Khayat.
Thank you very much, Lauren, and good morning, everyone, and thank you for joining us today. It's a great pleasure to see the conference series of Research Pays Off. So today I'd like to talk to you about this relatively new technology of compacted concrete pavement, which is another form of roller compacted concrete. I'd like to recognize the sponsors, Missouri DOT and National Road Research Alliance, mnroad, as well as the Tier 1 UTC recast, as well as my the project manager that was working at the time as a postdoc was me, Nima Farzadenia, who's now an assistant professor at the University of Alaska, Fairbanks. Right. So compacted concrete pavement, or CCP, is an advanced form of roller compacted concrete. I'll show more pictures about that and the difference between the machines that are used for compaction. But the CCP technology has a minimum rolling requirements to ensure that you have a good compaction of the concrete pavement, as well as good surface texture to improve the rideability aspect. The technology of CCP uses proprietary admixtures. There are two admixtures that are used. One of them is used in the mixture composition itself. Another one, what you see over there, that blue liquid, that is used as a finishing aids. And then because of the admixtures and the finishing aids, the concrete itself tends to have a longer workability retention, allowing longer time for consolidation and finishing. So on the left side, you have concrete pavement that are constructed using roller compacted concrete, heavy gyratory rollers that are going back and forth to consolidate the pavements. The surface finish is often challenging. You don't have a very good surface finish because of a lack of the mortar and the dry consistency of the RCC. The difference with the CCP is because the admixtures that are used, they bring water to the surface, and the finishing aid that eventually evaporate gives you a tighter surface, better rideability, and the equipment that are used for consolidation are a lot smaller, thus allowing sometimes contractors who do not have these specialty equipment to be able to bid and construct this type of pavement. And you could see even the finishing, equipment that are used here on the right. Now, before presenting two case studies that were done, one of them was Missouri DOT in the city of Mexico and Missouri, and the other one as a part of collaboration between mnroad and mndot in another place in Missouri, also CCP. I'd like just to go back and then talk a little bit about RCC technology in general. As you know, in the design of mixture design of RCC, we try to optimize the water content, the water cement ratio. In this case, it's shown as a water to solid ratio versus the density. So that density is determined using modified Proctor test. And then you see that the density, in situ density, increases as you add more water. It makes it more easy to consolidate, and you reach a peak, and beyond that, you're just adding porosity to the mix, and the weight is reduced. So 5.5% in this case is an optimum water content. We could also look at another sets of three figures, again doing the same thing, modified Proctor test. The difference between them is the binder content. So the binder content and the blue one is low, and the red one is medium, and the green one is high. So the binder content determines, and the water to binder ratio determine the amount of paste. So we can see over here that in terms of the optimum water content. It's about 5.5 to 6% consistently, but as you increase the binder content, you get higher density, but also higher compressive and flexural strengths. And this is some work we did before we worked on the CCP using RCC technology. We could in the lab use an ICT, intensive compaction tester gyratory that is similar to the one we use often in the asphalt industry. It's a smaller one with a cylinder of 4x8. And we apply a certain protocol of consolidation and determine the maximum packing density. And here we have a ternary diagram showing the sand, the coarse aggregate, and the intermediate grain size distribution between sand and coarse aggregate. And then the contours values are the values that are determined over here for the density. And we see that there are certain combinations where, sorry, this is the VB time, certain combinations that the VB time is reduced. So out there, the VB time, for example, is shown to be 30 seconds. In this region over here, it can get all the way to 80 seconds, 81 seconds, which is very dry consistency. And then this region here appears to be the optimum was the lowest of 31. So the packing density is very much affected by the combination of aggregates, as we know. And here you have on the bottom a very dry consistency. This is after consolidation using the VB test. And we could see that the VB time is greater than 90 seconds. And if it's that long, we just stop the test. And if we use this region with high packing density, we see the VB test is about 45 seconds. I'm saying all this because these numbers will come back when we look at the two case studies where CCP was used. The packing density that we saw earlier, this zone over here was the highest packing density, corresponds to a zone where the compressive strength was the highest. So samples that were molded and consolidated and subjected 28 days of moist curing attained higher compressive strengths in the zones that were also the highest packing density and the lowest VB time. So easier to consolidate, higher density, higher strengths. And you could see with the same water cement ratio, same binder contents, just changing the aggregate distribution and combinations, we can have strengths that are as high as 57, which is about 9,000 PSI, and as low as, in this case, 27, which is about 4,500 PSI. And looking at some of the literature for RCC, these are mixture proportion for RCC. If we look at, for example, CTL mixtures, some different state DOTs, you have South Carolina and Charlotte, Tennessee. And then we have on the very right, we have the Canadian PCA. But looking at them, you see that the binder contents, often it is about 500 pounds per cubic yard. In some cases, it can be 550. In this case here, 444. But 450 to 550 appears to be very consistent in using RCC technology. The maximum size of aggregate, you see that different values, 3/4 of an inch seems to be typical, in some cases going to 1 inch or 1/2 an inch. And then in terms of water to cementitious materials, you see the Canadians, where they air entrained the concrete, they lower the water to binder ratio down to 0.32. But here in the US, 0.42, 0.47, up to 0.53 seems to be consistent. And the compressive strengths at 28 days, you can get compressive strengths between 5,200 PSIs to about 8,000 PSI compressive strengths, and flexural strengths also between 640 and about 900 PSI. Now, this is important because later on we'll come back and look at the densities and the flexural strengths and compressive strengths, which of course are very much affected by the density and the compaction energy of the pavement. So the two case studies I'm going to present today for CCP, were constructed in the city of Mexico and Scott County in Missouri, and the mixture proportioning are shown over here. So for the first one, the contractor decided to use what I would say a lower end of binder content, and it's only type 1,2 cement, 450, and the other one, Scott City, Scott County, they used both fly ash, class C fly ash and type 1,2 cement, higher binder content. The water to binder contents you see over here, the first one is 0.52, which is on the high end if you look at other mixtures, and 0.38, which is on the very low end of the typical mixtures I showed in the previous slides. In both cases, they use this ACID Plus, which is a proprietary admixture that is used in the mixture proportioning. I do not have this value. I only have the value that was used in the first project. And in both cases, the maximum size aggregate was 1/2 inch, which is not very consistent of RCC technology, where most of the values are 3/4 inch. All right, so in the first project, MoDOT helped the city of Mexico to write a special grant for the use of innovative technology and emerging technologies. And it was a city street, Holt Street, that had to be repaved. This street sees a lot of trucking. There's a big factory over here, and sees a lot of heavy traffic, and they decided to use this technology. This was back in June 2019 when the project construction took place. Again, the mixture proportioning, I already showed it. 152 water to binder ratio, 450 cements, and 1/2 inch maximum size aggregate. And here are a couple of photos of the finishing. Again, the concrete paver laid out the concrete. Yes, I have a slide of it over here. And then the finishing was done using very small rollers, as well as ride-on finishing machines, as you would see in industrial floors. And the worker over here is applying this ACID finishing aid that is allowing some moisture to come to the surface and improving the surface texture. So on the left side, you have the surface texture of the concrete after the paver has passed and finished the surface, consolidated the surface initially. And this on the right side, you have the final finishing surface aspect after the application of the finishing aids and numerous passing of the finishing equipment. So at Missouri S&T, we worked with MoDOT to take many samples. We took samples that were used for compressive strengths and elastic modulus, and took some prisms also to evaluate flexural strength. So the prisms are 6 by 6 by 22 inches. Scaling resistance, the icing salt scaling, freezing and thawing, as well as drying shrinkage. So all these samples were taken to the lab and moisture in lime saturated water up to 220 days. And in terms of shrinkage, they were moisture for 7 days and then let to be air dried. The consolidation, if you haven't seen the consolidation of samples for RCC or CCP is very intensive. So this is covered by STM-C 1435 using probably a vibrating hammer, applying pressure and then casting them in 3 layers and applying pressure until you get a sample. Each sample takes about 5 minutes to prepare. It's a long process and it's labor intensive. Here also the sampling of the prism, the 6 by 6 inch prisms. Again, we consolidate them using this plate, vibratory plate, and then going layer by layer across and finishing it until we ensure that we have good density. Now in the lab, when we were doing this, we tried it on purpose to have different operators during the consolidation, and you get quite a bit of variability according to the operator. So whenever we did this sampling for the research projects, whether we're taking samples from 3 different operators, 2 different operators, 3 different operators, 4 different operators, 5 different operators, 6 different operators, 7 different operators, 8 different operators, 9 different operators, 10 different operators, 11 different operators, 12 different operators, 13 different operators, 14 different operators, 15 different operators, 16 different operators, 17 different operators, 18 different operators, 19 different operators, 20 different operators, 21 different operators, 22 different operators, 23 different operators, 24 different operators, 25 different operators, 26 different operators, 27 different operators, 28 different operators, 29 different operators, 30 different operators, 31 different operators, 32 different operators, 33 differ for any of the samples, we made sure that the sampling is done only by a single operator. So some of the compressive strengths, elastic moduli, modulus results, we see the results for on top are the cast in place samples, and at the bottom are the core samples. And again, they were tested at the age of 91 days, 120 days. And we see that, first of all, the coefficient of variability is quite low for the sampling, 5% to 12%, and for the coring. And these are within, good to very good values for repeatability. And we see that the compressive strength in situ was slightly lower, about 10% lower for 28 days if we compare 4,000 to 4,450 PSI, and even less lower than that going to 120 days. So this is within the 85% spread of compressive strengths, or 15% reduction when you have coring versus sampling, field sampling. However, in terms of flexure strengths, we see that there's a very high variability of the flexure strengths, indicating on one of them that the most probably the density of the compaction energy density of the sample was not high enough, reducing the flexure strengths and increasing the variability. And we can see also that measuring the hardened concrete density, we have 147 versus 153 pound per cubic feet for core samples versus in situ versus field prepared samples. And here we are plotting the force versus deflection to determine the flexure strengths of two prisms. And you can see that the so-cut ones are those two on top at 90 days. And then at 120 days, we have those also on top, the blue and the orange. And at 90 days, the samples that were taken from the field and consolidated properly were slightly lower. So all in all, there's not a lot of spread between the in situ and field prepared samples. We noticed that the flexure strength is lower than what you would expect. When I showed you earlier in the presentation, the table, we're talking about 640 up to 900 PSI flexure strengths. And here we have really half of those numbers. But again, the water to cement ratio, and there was only cement used in this case, no fly ash, relatively low cement content, and the water cement ratio was 0.52, which is on the high end. We did measure electrical resistivity, not because there's any risk of corrosion, but as an index of transport properties. And the values that are shown over here all indicate moderate electrical resistivity, what you would expect was the mixture proportion that was used. Now, we were interested in freezing and thawing, knowing that the concrete was not air entrained. Still, we were interested in knowing what would be the freezing and thawing. This is accelerated freeze thaw test, the procedure A of ASTM 666. That means freezing and thawing in the presence of water. So it's a severe test. And you have here in the red the average of 3 samples, and you have the relative dynamic modulus of elasticity that is determined using P waves. And then you see the cycles up to 200 cycles. We had a very severe drop of elastic modulus indicating internal cracking of the concrete because of repetitive freeze thaw cycles. So you could say that the freeze thaw resistance of a concrete like this is poor. Normally you would expect to have at least 60% residual elastic modulus after 300 cycles. And even in certain Nordic countries, like Canada, for example, they specify 80%. So this concrete was not air entrained, but it's very tight, watertight, but did not really withstand this accelerated freeze thaw testing. In terms of de-icing salt scaling, we did the ASTM C694 test. where we take some samples and pond them with sodium chloride solution for 50 days. We did the test for 80 days because we were impressed how resilient these samples were. And you could see that the average of 2 samples, there's quite a bit of spread, but the average of 2 samples, that the cumulative mass loss was still very low. We're talking the average of 200 grams per square meter. Many of specifications go up 50 cycles up to 1 kilogram, so 1,000 grams per square meter of scaled out material. So despite the fact that the concrete was not air entrained, the surface is so tight that there was no, and there's very little amount of paste, as you know, in RCC technology, that the de-icing salt scaling resistance was very, very high. We also measure shrinkage. I did not show the results, but the drying shrinkage was very, very low. This is after 120 days. No, after 70 days, 60 microstrain, which is very, very low shrinkage. Mechanical properties, we found out that they are similar to those that were field samples, indicating that this RCC mixture had adequate consolidation. We saw some weak signs of consolidation in some of the samples. I mentioned that in the flexure sample where the flexure strength was much lower than the companion samples taken nearby. The frost durability was very low, 30% residual strength, and the de-icing salt was very high, as we saw before. So this was the first case study, and then the second case study took place around the same time in October 2018. This was in collaboration with mnroad. So instead of having a panel, or in this case 3 panels, added to the mnroad site, discussions between Missouri DOT and mnroad was like, we plan to do this in Missouri, so can we instrument them and observe them and learn from that with this job that was taking place in Missouri. So you have in Scott County, Missouri, you have a road. This is a service road that is 4-inch aggregate base with 12-inch of lime stabilized subbase. The pavement thickness is 6 inches. And then we had 3 experimental cells. You have them here, cells 1, 2, 3. The difference between them, they all use CCP technology. The last one, we decided that we would like to use fibers, synthetic fibers, to see if we can reduce warping and curling, and we can improve flexure strengths and other properties in the presence of those synthetic fibers. So I'll talk more about how we decided on the use of 5 pounds per cubic yard of fibers. The panels had different lengths. So the panels or cells 1 and 2 were 500 feet, and the cell number 3 was with the fibers was shorter. The panel size 12 by 15 by 6 inches, both for cells 1 and 3. And then we wanted to compare the effect of the lengths of the panel, so 12 feet between joints versus 15 feet. So that's the difference between 1 and 2. So this is a mixture proportioning. In the previous case study I mentioned in Mexico City in Missouri, only used 450 pounds per cubic yard of cement. In this case, it was decided to use also fly ash, so a lot higher paste content, if you would, or binder content, but the water binder ratio was tighter. So instead of 0.53, it was reduced to 0.38. The admixture, the proprietary admixture that is used is ACET. It was used about 15 pounds per cubic yard. And these are the synthetic fibers. The synthetic fibers that were selected are the tough strand SF from Euclid Chemicals. And this is how the fibers look in the mixture after mixing. So this is a very, very dry consistency, as you could see. But this consistency is what was used for making the samples and for constructing those 3 cells. So the aggregate size distribution that was used and the combined aggregate size distribution. So the sand to aggregate turned out to be by volume 35%, the fly ash versus the binder 18%, and the mixture was not air entrained. It's impossible to air entrain something like this. We did quite a bit of testing using the equipment of the contractor and his sites. And as you can see here, this is Dr. Farzadenia, who was working with some graduate students in our team, made a lot of samples. We had 4 mixtures. The first one is a base mixture without any fibers. So the 0.38 water to binder ratio corresponds to about 6% moisture content. And this was again optimized using the modified Proctor test that I showed earlier, moisture content versus density. And the second one, in consultation with the Euclid Chemicals, we opted to start with 4 pounds per cubic yard based on experience with concrete pavement, but concrete pavement was 1.5 to 2 inches in consistency. This is zero slump, as you know. And then we went to 5 pounds, and then went to 6 pounds, but we found out that the mixture was extremely dry, and then we had to increase the water content a little bit. So 6.5%, 6.25% moisture content. The final option was to opt for mixture number 3. I'll show you why. So this is mixture number 1, no fiber, 4 pounds, 5 pounds, 6 pounds per cubic yard. And you see the compressive strengths are increasing, but at a certain point, there's a lack of consolidation. The mixture is very, very dry. And this one here, we only got 1 sample. The other one, the density was very low and the strength was very low. We did also the flexural strengths. We're interested in the residual strengths at the deformation of lengths of the sample between the 2 supports over 150. Experience from previous testing told us that we need to get at least 20%. So you could see the load deflection. This is typical of synthetic fibers. Once you reach the peak lengths, you have a very fast and sudden reduction of load carrying capacity, but the fibers are still sustaining some load, and so you still have a lot of deformation and bridging the cracks. So if you look at very, very close, the initial part of this curve over here, that's what is shown on the right side. You have mixture number 1, which does not have any fibers. And once you reach ultimate flexural strengths, you lose capacity immediately. And then you have mixture number 2 was a 4 pounds. The number 3 was 5 pounds, and number 4 was a 6 pounds per cubic yard. And you see that the load deflection and the gradual reduction of load carrying capacity. So flexural strengths, the mean flexural strengths, 620, 640, drop to 530, and then increase to 620. And the residual values, if we were to look at L over 150, again, I was looking for, we were hoping to get 0.20, but we got the highest was 0.16. So given the consistency of the mixture, the mechanical properties, decision was made to use the mixture that had 5 pounds per cubic yard. And this is the mixture that finally we used. So moving to the job site, we did 1 day of a lot of testing of mixing, placement, consolidation, and to adjust really the placement and consolidation energy. We measured the law of density using a nuclear moisture density gauge and different number of passes of this small vibratory roller, which is 2.5 tons. And then you see the paver. And in some cases, especially near the edges where we did not ensure good consolidation, we really had a crumbling structure. So all of that was used for adjustment of the placement parameters and the consolidation parameters. So this is the test strip, and you see in some cases there were adjustments and hand finishing A lot of trials, we learned a lot from that. And finally, the mixture was adjusted, going down from the 0.4 was 6 pounds, 6.20, 6 pounds per cubic yard to mixture number 4, which is 0.38 with 5 pounds of cubic yard. All in all, that's a mixture that gave us better performance. So the next day we moved into the actual placement of the 3 cells. So you have the skilled mixing equipment, plug mixer, dump trucks. See the consistency of the concrete is very, very low. Delivering it to the back end of the paver, and the paver over here is delivering is casting those cells. And again, those cells are in terms of width, they were 12 feet. So they did 12-foot strips, and this is one direction. And then later, when the project was finished, they came back and did the other strip to finish the other direction of the service road. So the compaction was specified. You consolidate, you compact it until you reach a density, in-situ density of 95%. And this was done. And then you have this admixture, which is the finishing aid, proprietary admixture that was used. And you could see that the pasty type of apparent, this is without it, this is with it, and then the riding trowel are going around, ensuring that we have a closed surface. And then curing compounds was applied, and that's how the concrete was cured. In parallel to the placement, our research team for Missouri S&T was there doing a lot of testing, including the VB test. And you can see the VB test over here in the procedure. So you consolidate it over a vibrating table with an overhead load of 50 pounds. And then normally we stop the consolidation or the vibration once there's a hollow of, so there's a plate that is on top. And once we see a hollow of mortar seeping up, we say, okay, this is a time of ultimate consolidation. Unfortunately, that was not achieved. In both cases with the CCP mixture and the fiber CCCP mixture, we had to stop the test after 60 seconds. So we can consider this the same thing what we saw in the Mexico test, that both of these CCP mixtures, in my opinion, were too dry. The consistency was not high enough. So, and we saw earlier if the consistency is moderate, like 45 seconds, you get higher density and you get higher compressive strengths out of your strip. So sampling, again, the sampling was done on the 6x12 samples and the prisms, very labor intensive. And later on, with the support of our sponsors, we went back and took a lot of samples for mechanical properties, and then we cut many samples for flexural strengths and frost durability, as well as shrinkage. So this is the schedule of all the sampling that we took. You can see that we even looked at air void distribution, RCPT, and all of that is reported in the report. And I know that you have access from the link, you have access to the final report. I'm going to present some of these results, but you can see extensive amount of sampling. So starting with the compressive strengths is reported here at 91 days. The samples were always maintained moist cured, even when we brought them back to the lab. And you see that the field cast samples, coefficient of variations are very, very low. This is really impressive. I showed you the energy of consolidation, how intensive it is, yet we get very good consistency in terms of testing. These are averages of 3 samples. So compressive strength 3,300 PSI, 5,100 PSI, no fibers with fibers. So we could see that the fibers, which is unusual for fibers, but they improved quite a bit the compressive strength of the concrete. And they also improved quite a bit the compressive strength of the concrete that was from the core samples. But one thing we see here is a very large drop between the in situ core versus the field prepared samples. And that is, again, an issue with the consolidation of the concrete. So the CCP technology in this case gave us a very nice surface finish, but the consolidation in this case was not really adequate, unfortunately. In terms of flexural strengths of the cast in place samples, again, 7 days, 28 days, very typical load deflection. You lose a lot of load carrying capacity. This is without any fibers, and with the fibers, you get a small residual strength, less than 0.20% at a very high deflection. So again, at 7 and 28 days. So if we compare the flexural strengths, so we have the CCP 435 flexural strengths, residual strengths, of course, 0%. With the fibers, you have a slight improvement, about 10%, but the main improvement was the load carrying capacity at L over 150. We got 15% residual strengths. And this is at 7 days, and similar results at 28 days. So at 28 days, the flexural strength was similar with and without fibers. But again, we have that residual strength, that 12% with the fibers. So you can look more at the results of 91 days. So field cast versus saw-cut samples. We think as a main conclusion that the lack of proper consolidation of the pavement reduces the flexural strengths and the effectiveness of the fibers. The fibers from the initial testing, we saw-cut the samples because of the very, very dry consistency of the concrete, despite the fact that it's subjected to intensive consolidation. We felt that there was not enough bonding between the cement paste and the fibers to really activate and take advantage fully of those embedded fibers. The electrical resistivity, again, you see bulk electrical resistivity and the surface. We tested those with and without fibers. And you see that one was the fiber, the resistivity was lower, indicating maybe some issues with the bond interface, both for the bulk and the resistivity. So fibers slightly decreased electrical resistivity. And we think that it's because of the dry consistency, probably lower compaction, but also the lack of good transition zone between the embedded fibers and the cement paste. And the same story repeated of what we found out about freezing and thawing resistance with the CCP that was used in Mexico City. So if you look at the average of samples, you see that the very, very sharp drop of freezing and thawing after 225 cycles or 220 cycles. Durability coefficient is very poor, only 20%. And this was for both samples that were molded in the field and the prisms that were extracted by saw cutting the pavement itself. And the de-icing salt scaling, we found out very similar results, very little de-icing salt that was observed after after 50 cycles. So 0.2 or 1,000 grams per square meter below the range. So the values actually were 500 grams, and despite the fact, and we extended that to 80 cycles. Drying shrinkage, so 7 days of moist curing followed by dry curing in 50% humidity, constant temperature for 180 days. You could see that there's very little amount of shrinkage, but one thing we see that here is the sample 1, sample 2, sample 3, huge variability. And these, again, very large variability of samples that these are saw-cut samples, indicating also that inconsistent consolidation of the concrete. And on the right side is the drying shrinkage that you for field samples that were consolidated by hand, so more consistent consolidation. We also looked at the curling and warping using a simple procedure that was developed and provided to us by Iowa State University CP Tech Center, Dr. Peter Taylor. So what we do is we measure the deflection between a certain point A and point B in a transverse direction, longitudinal and diagonal. And we look at that at 1 to 2 inch intervals. So between column A and column B, we look at the deflection that can be due to warping and curling. And what is shown over here is the difference between cell number 1, which is 12 feet in length, versus cell number 2, which is 15 feet in length. Both cells number 1 and 2 do not have any fibers. These values that are here are the deflections that are between station A and station B in all directions, longitudinal, transverse, and diagonal. What we are doing is we are comparing the difference between those stations, between elevations, for the 12-foot panel, long panel versus a 15-foot long panel. We could see over here that the 15-foot long panel, the difference between these two vertical lines is slightly higher than that of the 12-foot panel. That means warping and curling were higher in the 12-foot panel, in the 15-foot panel than the 12-foot panel. And that increased also with time. So we did this in 2018 in December, and we did this in September 2020. And we see with time that difference between the vertical two lines, 15-foot panels, increase with time. Okay. So indicating again higher amount of curling and warping with the 15-foot panel versus 12-foot panels. Neither of them has any fibers. And then this next slide compares cells number 1 and 3. Cell number 3 is made with fibers, and both of them have the 15-foot lengths. And we could see that the deflection with fiber at initial age was much higher than that without fibers, same lengths. But the difference between them with age seems to be decreasing. So the difference between the horizontal lines did not change much, but the difference between the vertical lines changed a little bit. So we can conclude from that is that the use of fibers seems to restrain curling and warping in the long run. And then there's no change in the range of deflection between the red line. Yeah, this is what it means. We also, with the help and the lead of mnroad team, did a lot of instrumentation of the 3 panels. So the instrumentations involved using a joint opening block at the joint opening between cells, vibrating wire gauges that measure temperature and strain, dynamic strain gauges, and a tree over here with sensors, 8 sensors for thermocouples. A data logger and a solar panel were installed, and this was obviously done before the placement of the pavement. So this is a diagram of some of the instrumentations. Again, at the joint opening, we have the joint opening block, vibrating wire strain gauges, thermocouples, everything channeled to a data acquisition system. We also, with the help of Missouri DOT, did actual testing using a truck that was calibrated and rolling here at different speeds, 10 miles per hour, 20 miles per hour, 5 miles per hour, and static. And we picked up a lot of deformation, and the analysis of this is all in the report. So this is cell number 1 with fiber and cell number 3 with fibers. Let's see. No, cell number 3 is with fibers, cell number 1 without fibers. Sorry. Unfortunately, a lot of the instrumentation that was installed got destroyed during the placement of the concrete. This is very, very dry consistency with the paper going over it, and then the consolidation that followed. So we had a low mortality rate, and we're able to pick up the signals with only very few sensors. But from the testing, what we learned is that the fiber really had no significant effect on the dynamic loading, with and without fiber. So this is without fiber versus with fibers. Did not seem to have any positive effect. So what we could learn as a conclusion from this second case study is that the use of fibers slightly increased compressive strength, actually considerably increased compressive strength and flexure strength at a certain age, but not later on. But improved the flexural toughness, and you saw that the residual strength was about 15% versus 0 without fibers, and then contributed also to reduction of shrinkage. Because again, the CCP, despite the mixtures, the admixtures that improve rideability and surface finishing that are very positive from constructivity point of view, I would say the mixture proportioning itself was too dry to start with. And then we were not able to really learn the maximum potential of the CCP technology, combined with an RCC that is properly designed and properly consolidated. So the CCP and the fiber-reinforced CCP exhibited moderate to poor frost durability, but very good resistance to de-icing salt. And then finally, the use of fibers seems to reduce the curling warping evolution with time, which is a positive indication and probably warranted more investigation in the future. So this job would not have been possible without the help and the support of Tom Burham from mnroad, mndot, and Jen Harper, Brett Trotman, and John Donahue from mndot, who are very, very supportive in all aspects of instrumentation to field testing to different type of testing that followed also in the field. So with that, I'd like to stop and be happy to take any questions you might have.
Great, thank you so much. The first question we have in the chat is, will the presentation slides be available to download or email out?
So what I can do is I can put it in a PDF and send it to you, Lauren. And then
yes, that sounds great. And I will make them available then on our website as a PDF. So we can arrange that, yes. And then we do have a few questions and comments here, and so I can go through and read those for you,
Sure.
Unless the person who asked them wants to chime in and ask them themselves, but I can just go ahead and do that. Based on what standards was this research designed? Are there any standards for CCP?
I would say no. These are proprietary mixtures that were provided in both cases by the contractors. We had with Missouri DOT going many years back, we had a lot of discussion with a company that was trying to promote in our region CCP technology and try to understand the ACID and how it works. And I know that they did some testing with different researchers, different labs around the country. Some of the results were available to us. But in both cases, really, we were not involved in the development of the mixtures. We were involved and wrote 2 big reports as part of the recast project or RCC technology. And the earlier slide that I showed was the packing density and its effect on properties were all done in the objective of how to better design durable RCC pavements. So for the CCP, both case studies, it was from the experience of the contractor that they proposed this mixture proportion. The only thing that we intervened in the second mixture is we'd like to test the fibers, and then we worked on trying to optimize the consistency and the properties that would tell us, is it 4 pounds, 5 pounds, 5 or 6 pounds of per cubic yard of fibers.
Okay, so hopefully that answered the question. So the next one here is a little bit long. It's a few questions in a row. What was the percentage compaction measured in the field after the rollers? Also, was the density measured using direct transmission down to at least 75% of depth? It doesn't appear as though the small roller was enough to get proper compaction through the entire depth as shown by the field saw cut samples. Is it recommended that the proper roller is used to achieve compaction through the entire depth of the pavement?
Yeah, very good question. So we know from RCC technology that the consolidation is extremely important, and that's measured by by the nuclear gauge device. The specification was attaining 95% of maximum density. That was what, and that's the testing that was done when we did the strip test, and then trying to adjust the mixture itself and the placement and the consolidation and the number of consolidation rolls back and forth to achieve that. We noticed that we were not getting this consolidation at the edges, and then the procedure had to be adjusted. The thickness is only 6 inches. So the contractor thought that he could achieve high consolidation using the equipment that were specified, given the limited thickness of this pavement. But obviously, from the results and the large spread that we observed from the shrinkage tests and some of the flexural tests, and the density itself, that the consolidation was not very adequate. So it's a combination of consolidation and mixture proportioning. So the mixture proportioning was extremely dry, obviously, and the consolidation, in my opinion, was not adequate. I hope I
yeah, then someone kind of responded to that set of questions by saying, correct, the density data showed a major issue in the research, starting with the method of construction and sampling.
Yeah.
Then we have another question here. Do you think the fibers aided in joint load transfer? Has a joint faulting started yet?
Last time we inspected this pavement was a year ago. We didn't observe any joint faulting. Unfortunately, mnroad installed some instrumentation across the joint to look at that aspect, and that was one of the mortalities. But visual observation a year ago, we didn't see any joint faulting yet.
Okay, and I would assume that this would be somewhere where we also take drone footage over mnroad, and we're having that done twice a year, so that we may have actual videos. If you haven't personally been out there for a year, we may have other videos that may show something else too. I know I'm not sure how effective they are at being able to see, everything from up above as opposed to standing a little closer.
Yeah.
But we can maybe, I know we're still trying to kind of organize all the videos into the different projects that they are related to. So then we have another comment here. There's tremendous advantage in CCP providing a surface you do not need to diamond grind for texture. Could you kindly comment on the extent of deployment of CCP? Are proprietary issues placing a stranglehold on deployment, or is it not technically, in your opinion, ready for prime time?
Yeah, frankly, I cannot comment on this. My experience with CCP stops with the 2 projects I was involved in. I know that there was a great benefit to see the surface texture, and I don't think that the issues here are because of the CCP technology. I think the issues that we observe in these 2 case studies is because of the mixture proportioning and probably the combination of the consolidation energy given that mixture proportioning. Title of this seminar is Research Pays Off, and this is research in progress. I don't think we can say from this, no, it doesn't work. there's a lot of benefits that I can see from this in terms of rideability. And we know that in concrete pavement, in the past, for example, RCC in Missouri has been used for shoulders pavement and not the main pavement. In other places around the world, it's used for secondary roads, like, logging roads and what have you, because of the surface texture. I think this is a great improvement. We should embrace it, and would love to hear more case studies from people who apply this. But I think adjusting the mixture proportion of what we know of RCC mixture proportion, and again, we were not able to use that knowledge because this was a big job using proprietary mixtures. But if we were to apply our best knowledge collectively with RCC mixture proportioning, and I think this technology is here to stay, in my opinion.
Okay. We are getting a few more questions and comments, so we'll try to get through them quickly here. Given that the admixtures did not allow the pavers to achieve greater than 98% compaction with the paver machine alone, as claimed by CCP, can we stop calling this CCP and call it RCC with a trowels finish?
Fair enough. It's an RCC with modified consolidation.
All right, next question is, do you believe galvanized steel fibers or basalt fibers would be worthwhile for a better trial for toughness gain?
I mean, I think definitely there's more room for fibers and concrete pavements. But I think regardless of the fibers, we have to work on the consistency of the mixture to ensure that we have good consolidation and good bonding to the fibers, so we can really activate the fibers. But there are different types of fibers, whether they are metallic fibers, galvanized fibers, basalt fibers. I think there's room for all of the above in pavement construction. But we still would like to learn if the use of the fibers in proper, when we are satisfied with the mixture and the consolidation, how much are they adding to reducing curling and warping and joint faulting and load transferring and cracking because of shrinkage or other type of, So I don't think we from this job here we learned what we need to learn about the potential benefits of using fibers and RCC technology.
Okay. And then I have two more comments I'll just read so that everybody can hear it. It should be noted that a troweled finish is now more common than a natural finish for RCC pavements. In addition, there are many different admixtures available on the market to achieve a troweled finish. And then the last comment here is most of the project was diamond ground to achieve a good ride quality, so the surface texturing was a moot point.
Thank you for the comments.
Yeah, anything else you would like to share or just wrap up for us?
I just would like to thank you, Lauren, for organizing this. This is very, very interesting series of lectures that you guys have. Research pays off. Mm-hmm. It really pays off. And then, so this is, again, a very nice collaboration, thanks to the engineers from both DOTs. And I think we can all learn from these large field trials, putting what we learn, to practice and try to hopefully get them in guidelines and standards in the future, so we can all improve on the quality of our infrastructure. So I'd like to thank you all for attending and for organizing this, and wish you happy holidays and happy new year. Mm-hmm. I hope to see you at the TRB.
Yes. Yes, thank you, Kamal, for your time this morning, and thank you all for the active chat with questions and comments. And I'm seeing a few people saying thank you, great presentation. So yes, thanks for attending and joining us today, and we will hope to see you next month, and hopefully you all can connect at TRB as well. And we will get the presentation file up on the website here soon, so you can check back for that soon as well. Thank you, everyone. Have a great holiday, and we'll see you in the new year.
Perfect. Thank you.